Okay, so today we're going to talk about the parallel axis theorem, one of those topics that's 80% of the final exam. Our learning objectives is to define what the parallel axis system allows us to calculate for a composite shape, know and implement these equations. We'll talk about those equations, and then being able to calculate the centroid axes for a composite shape. That's back finding x bar and y bar. We've done that before, but just we need to be able to do that here as well. And then label these distances d sub x and d sub y. This is not a differential dx and dy. It's a distance that we'll talk about doing on our composite shape. You do have a homework problem that talks about the polar moment of inertia, J. This is it really, if we can find Ix and Iy, we can find J, because J is simply just Ix plus Iy. So just all you need to write down is that J is equal to Ix plus Iy for this one. That's really all we're going to talk about for the polar moment of inertia, is that it's just Ix plus Iy. And then our homework problem number 2, you can see it's a composite shape, and it's composed of 2 rectangles. Well, if we can find the moment of inertia for each rectangle, then we can find the moment of inertia for the composite using the parallel axis theorem. Homework number 3 is a shape composed of 3 different rectangles that we could break up into 3 different rectangles. And again, if we can find the moment of inertia for each rectangle, we can find the moment of inertia for the composite. A reminder about some resources for you all as we move into the finals and the end of the semester, which we know can be a stressful time of the semester, but let's take it one step at a time. And if you need help, lots of resources are out there. CARE at Mines, CASA, the Counseling Center, the Health Center, Colorado Crisis Services provides 24 hours, 7 days a week. And of course, if there's an emergency, you call 911 rather than calling one of these other help services there. Okay, let's talk about the parallel axis theorem. And so we saw from the homework there that it's all about being able to find what's going on for a rectangle. And then our composites just include multiple rectangles together. So let's start actually with a drawing of a rectangle, just like we saw in the quiz. We are always going to refer to the horizontal dimension will always be B. And the vertical dimension is always going to be called H for us. So we have a B and we have an H. If we go to the centroid of that shape right there, let's call that X prime and Y prime for the centroid of that rectangle right there. Well, this is just always for a rectangle. We can find the moment of inertia about the centroid, Ix prime, is equal to 1/12 BH cubed. And this is just something that we have to remember or to be able to look up during an exam or when you're doing the homework. It's found by doing integration. We could go through and derive it, but we don't need to. We just need to remember these equations. Iy prime is 1/12. And actually, before I fill out the rest of it, let's go back and think about conceptually the moment of inertia. It's the second moment of area, right? And if I pull out the area out of this, I have B times H. And so this is the area of that rectangle is B times H. And then, right, just rearranging that formula there, wouldn't it be the area times H squared? Now, which dimension describes how far away we get from the X prime axis? It's the H dimension. that describes how far we get away from that axis. So remember, it's the second moment of area, and area further away from that axis means that our moment of inertia goes up. It's higher. It's a larger bending stiffness. So just like with this, I can bend it in that dimension there, but I can't bend it in this dimension. And that's because I have more distance away from the centroid of the rectangle. And so we have the area, and then this h squared, this is really the moment arm squared. This is our second moment of area, right? So this is our second moment because it's h squared. And so we have area times h squared. So what do you think Iy prime is going to look like then? Isn't it going to be the area times whatever distance describes how far we get away from the y prime axis? And so that's going to be a b cubed times h. Yeah, absolutely. Nice job. I saw a bunch of those show up in the chat. So we can always just take these for a rectangle about its centroid. And so I x prime y prime would be what then? What's I x prime y prime for this rectangle? Anyone? 0, right? Yeah, this is because we have symmetry. And so our I x prime y prime is equal to 0, always for a rectangle. I guess I need to add something here about the centroid, about its centroid. We will find these will always hold here. So 1/12 bh cubed, 1/12 b cubed h. Now, what the parallel axis theorem allows us to do, so our equations for the parallel axis theorem these say that we can find the moment of inertia about any other axis. Let's say I put another axis, let's say I put it right here. So let's call this one an x-axis. And we can call that one a y-axis. So we can find, and I'm going to color code this, Ix, and so that would be the moment of inertia about the x-axis, is going to be equal to I times our x prime plus the area times the distance between x and x prime axis. Well, what's the distance between the x and the x prime axis? It's a y distance, and that's what we've referred to as d sub y. So times a d sub y. Now it's the second moment of area, so it's dy squared to make sure that we keep our units consistent here. We can find I y would be equal to I y prime plus the area times d sub x squared, where d sub x describes the distance between the y and the y prime axis. So there's our d sub x. So that means we can use the parallel axis theorem. If we know our 1/12 equations, we can find what the moment of inertia is of that rectangle about any other axis that's out there. I x y is going to be equal to I x prime y prime plus the area times a d sub x times d sub y. And so these ones here, these are for the centroidal axes. And the red axes, these are for any non-centroidal axes. And yes, area A is the area of the rectangle. So A is equal to B times H. It's the area that we're transforming. A parallel axis theorem is really a transformation between axes that are parallel to each other. So we can go from one x prime, y prime axis to any other x, y axes. Now, the signs on dx and dy, they don't matter if we're doing ix or iy, because it's squared, right? Dx and dy are squared. They are based on the x, y axes. So based on the red axes. And we just need to say, what are the coordinates of the blue axes? We need to ask ourselves, so what are the x and y chords or coordinates of the x prime, y prime origin? So if we look back up to this right here, to this picture, what is my x coordinate and y coordinate with respect to, in the x, y, let me do it in red, in the x, y axes. Wouldn't that be, if we think about this location C, what are the coordinates of the location C? Is it a positive x or a negative x? Does it have a negative x coordinate or a positive x coordinate? Let me see somebody in the front row. I see Leah, you've got your camera on. What's the x coordinate? Is it a negative x coordinate or a positive x coordinate?
Positive.
Okay, so remember it's relative. So it's kind of weird because it looks like the x prime and the y prime are like the global coordinate system because they're in the middle of the rectangle. But actually the red is our global coordinate system. Oh. It's actually based on the red axis. If we look in terms of the red axis, isn't it a negative x? Does that make sense? Okay.
Yeah.
Right. So it's a negative x. And then relative to the red axis, it's a positive y. So a little bit weird to think about that way because it's like you think about the blue axis as kind of like the center of the universe, but it's actually the red axis is like the center of our universe. So it's those red axes that will always be the center of our universe. And that's our global coordinate system. And then the blue axes will be our local coordinate system. Okay, did everybody get that down? A negative x and a positive y. And so actually, let me fill this in. That means we're going to have a negative dx and a positive dy is what we'll end up with for that particular picture. And we're going to jump into an example where we'll look at that more. Okay, our example problem today is actually part of an example that I do actually from a project that I work on. I also do this in my concrete design class as well, but it's all the it's part of the design of all the slabs in the Coors Tech Center, in Marcus Hall, and all those places where they have that form decking. And we basically, that form decking creates a T-shape. So we have a concrete section here that we're going to pull out, and we want to figure out for this concrete section, and this has a dimension up here of 12 inches, and then this is 3 inches. This down here is 5 inches, and then the height right here is equal to 2 inches. And we do have symmetry here, where this is a line of symmetry right there. And so what we want to find for this is we want to find Ix, Iy, and Ixy for the composite centroid. Which, if we were designing that floor slab, we would have to figure out Ix and Iy and Ixy to be able to calculate the deflection and make sure that it's not going to deflect too much, and that it's going to, you know, where people don't feel like, oh my gosh, this floor feels like it's about to collapse, or the floor feels unstable. So we want to do it, we want to figure this out for that composite centroid. And let's just go ahead and let's, you know, we can call the composite centroid X and Y, and we're going to use the red axis, which would probably be about right here or so. And so we're going to call that X and Y, and that would be the centroid of the composite right there. We are only going to be, good question, Kalev, working with other shapes. There's some kind of general, on the homework assignment, you saw some kind of blob looking things that didn't have like a shape, and so we have to use concepts to figure that one out. And then there are, I think there is a homework problem with a circle. And so yeah, for anything that's not a rectangle, we can look, we would provide that with an exam, or you can look it up in the back cover of your textbook. So if you go to the back cover of your textbook, it has these shapes on there, and it has the moments of inertia, and for those, for any other shapes that you encounter on the textbook, or I'm sure you could look that up. So yeah, good question. Okay. So let's go ahead and let's draw a nice big picture here for our solution. So we're going to redraw that picture, but we're going to draw it nice and big because we need to label quite a few things on here. So let's see, it's 3 inches, 1, 2, 3 inches right there. And then let's see, 5 minus 12 is 7. So we go like 1, 2, 3.5. This is going to be 12 across there. We're going to go 2 inches down like that. So let's see, we got 5 inches. Should get us to there. And then another, there's our composite shape, a bigger picture of this that's relatively to scale. And the reason that I want to draw this bigger picture is because we are going to need to annotate a bunch of our dimensions on here. So we're going to start by breaking this up into rectangles. And so we know that for the centroid of each rectangle, and I'm going to continue using blue, for the centroid of each rectangle, we know the moments and products of inertia about that axis for each segment centroid. And so we can call this one here, let me call that one X prime, just to be consistent with my notes here. I'm going to call it X prime 1, and this would be a Y prime 1. And that's the centroid of that first area. So we're going to call this one A1. And then this bigger area up here, we'll call that A2. And A2, the centroid would be right there. And so we would have an X prime 2 and a Y prime 2. And then off to the side here, why don't we write down our steps for solving this problem here. So steps number 1 was to draw the X prime, Y prime axes. Okay, so we did that. Now the reason I like to start with that is because isn't our centroid of the composite going to be a weighted average of those two centroids? And so that means it has to fall somewhere in between those two centroids, right? It has to fall somewhere between the X prime 2 axis and the X prime 1 axis. And isn't it going to be closer to whichever one is bigger because it's the weighted average? And so let's do a red coordinate system. Like right in the middle would be about right there. So I want to go closer. So I'm going to draw it up here. We know it's going to be closer to that one. So there's our x-axis, and there's the y-axis for the composite centroid. So then our next step there was to draw the x, y axes. And remember, x prime, y prime, those are the segments. And our xy, that's the composite centroid. So once we draw those, we can start to look at things like, okay, well, how are we going to find our composite centroid, right? We don't know where the composite centroid is. We know where the centroid of each segment is located. And let's get our geometry up here. Like this is 3 inches right here. This whole distance across here, well, we know that is 6 inches. And then this one over here would also be 6 inches. And that's because we know that we have that line of symmetry. And notice that all those y-axes line up on one another. This distance across here is 5 inches. And then the distance coming down to here is equal to 2 inches. And so, you know, do we know where x prime 1 y prime axis is? Isn't it, you know, relative to the 2 inches, wouldn't it be 1 inch from the top of the bottom of that rectangle? We know where the x prime y prime 2 axis is located relative to all those dimensions. We do not know where xy is. And they typically give us in these problems on that homework, they will tell us where to measure things from. And actually, they're going to tell us that this is our y bar, is the distance measured from that top right there. So this distance over here is y bar. Well, remember to find, to find y bar, we said that y bar is equal to, you go back to our centroids of areas, it's y tilde 1 times a1 plus y tilde 2 times a2 divided by a1 plus a2. And so this is just our weighted average equation. Is how we find that y bar. Now, the only thing we have to watch out for is that y bar and y tilde are measured from the same place. And so y bar is measured from the top. Well, let's measure y tilde also from the top. So that would be y tilde for segment 2. And this would be y tilde for segment 1. So what is y tilde for, so actually let's go back up to our steps up here. I think, what did we do since we drew the XY axes? We labeled, or we added the dimensions for our y tildes and y bar. And then step 4 here, we need to find the values the y tilde values. And I guess, and the area, and A1 and A2 as well. So y tilde 1 is going to be equal to what? I think we should be able to find that based on our dimensions here. Let's see, who else is here? Oh, Colin. Colin, what do you, y tilde 1? What's that distance in inches? Oh, 4 inches. Exactly, right? Because we got 3 inches here, and then we're halfway along this 2 inches right here. So it's 4 inches. Okay, how about y tilde 2? Y tilde 2 isn't half of that 3 inches, so it's 1.5 inches. And then we can find A1 is going to be equal to 2 times 5 or 10 square inches, and A2 is going to be equal to 3 times 12 or 36 square inches. And so now we can find, we plug this all in for y bar, we're going to find that y bar is equal to 2.04 inches. So that's the weighted average stuff. This is all really a review. We have done this stuff before. For finding the centroid of that area. Okay, and then so that leaves us step number 5. We can calculate y bar. Okay, the next part of this is it's really handy. We have kind of a lot of stuff going on, and it's really handy to use a table. And so let's use a table for the parallel axis theorem equations. And if you look at go back to the parallel axis theorem, what do we need in there? Well, we need for each segment, and we have 2 of them. We have a segment 1 and we have a segment 2. Well, we need things like B and we need H. There's some basic stuff. And actually we've used B and H already in calculating our areas. Well, area is another one that we need. We need our area in the parallel axis theorem. The other thing that we need is those Ix prime, which is our 1/12 BH cubed, and Iy prime, which is the 1/12 B cubed H. And then we also will need here, we need our D sub X, and we need D sub Y for each of those segments. That'll include everything that we need for the parallel axis theorem. In general, the parallel axis theorem, like for Ix is equal to Ix prime plus a dy squared, right? So we need X prime, we need dy, we need area. In order to find area, we need B and H as well. Let me see if I can, I'm gonna move this down below our table so we can look at it while we fill out our table here. Yes, segment 1 and 2 are referencing A1 and A2. So those are our rectangles that we're referencing. Yep. Let's zoom out just a little bit so we can see that. Okay, so for segment 1, that's the bottom rectangle. B is 5, H is 2, our area is 10. We already figured all that stuff out. We can plug in our 1/12 BH cubed. We're going to end up finding 3.33. Our Iy prime, if we plug that in, we're going to end up finding 20.83. Let's go ahead. We'll come back to dx and dy. Let's finish these first 5 columns here. For area 2, B is 12, H is 3, area is 36. If we plug in into the 1/12 equation, we're going to find 27. We plug in to the IY prime equation. We're going to end up finding 432. And we can throw some units on these. These are inches, inches, inches squared, inches to the fourth, inches to the fourth, and then dx and dy are going to be in inches and inches. So now we got to figure out dx. Dx is the distance between, like for segment 1, it's the distance between the between the y and the y prime 1 axis. Well, that's 0 for this one. And it's also 0 for segment 2. That's because all the y-axes line up with each other. dy is the distance between the x prime 1 and the x-axis. So that would be this distance here. That is dy for segment 1. This distance here between x and x prime, that is dy for segment 2. The way that I like to find dx and dy is by taking, like, well, we already did dx. dy for segment 1 is the difference between y bar and y tilde 1. dy for segment 2 is going to be the difference between y bar and y tilde 2. Because if you look at the picture here, if we know, right, we know y bar and y tilde, they're all measured from the top of the rectangle, right? They're all measured from up here. And so if we wanted to find this dy1 that's down here in purple, couldn't we just take y tilde 1 and it's that whole distance and the difference between that and y bar? And so we had found over to the left over here, we had found y tilde for segment 1, we had labeled as 4 inches. Y tilde for segment 2 is 1.5 inches. And we know that y bar is equal to, what did we find it was equal to? It was 2.04 inches. Now, I say difference, and I'm using this term difference because that doesn't have a sign associated with it. Our sign is going to come from the picture. So then we're going to get the sign. We'll get our negative and positive from the picture. So dy1, what's the difference? Remember, I'll write it over here. Y bar is 2.04. Y tilde 1 is 4. Y tilde 2 is 1.5. What's the difference between y bar and y tilde 1? Anyone? And thinking about this is like an absolute value, right? It's yeah, 1 point, thank you, Morgan. It's 1.96. What's the difference between y bar and y tilde 2? Y bar and y tilde 2, isn't that equal to 0.54? Right? Y bar is 2.04, y tilde 2 is 1.5. So I'm just using these here. These are really just telling me the values of dy. The signs we'll get from the picture, because remember, the red axis is our global axis. So dy the coordinate, I'm going to circle it in red, the coordinate of that point right there, is it a negative y coordinate or a positive y coordinate relative to our global red axis coordinate system? Is it negative or is it positive? Remember that this is the center of our universe. The x, y, red axes are the center of our universe. So doesn't that mean that this would have a negative y coordinate? Yeah, right? So that's a negative. So that tells us that dy1 is negative. So this one is negative. dy2 is up here. This one is positive. So dy1 is negative 1.96. dy2 is positive 0.54. I kind of lost track of our steps here. Step 5, or did we already do, were we on step 6 now? We're on step 6. Step 6 is the table. And then maybe like step 6b is the diff for dy, for using the dy. Step 7 is going to be to plug in our values. For ix and iy and ixy, because now we have everything that we need. We can find ix, and so this is really what we're doing here, is we're finding the moment of inertia about the global coordinate system. The red axis for segment 1 is going to be equal to ix prime for segment 1 plus the area of segment 1 times d sub y1 squared. So that's going to be equal to 3.33 plus a1 is 10 times d sub y1 is minus 1.96 squared. And so we're going to get ix1 is equal to 41.75 inches to the fourth. So that is only for segment 1. So that's taking segment 1, that little rectangle on the bottom, and finding what's the moment of inertia about the red axis of just that rectangle. We need to do the same thing for for segment 2. And that's going to be equal to ix prime 2 plus a2 times the d sub y2 squared. And so that's going to be 27 plus 36 times 0.54 squared. And we're going to find that I for x2 is equal to 37.5 inches to the fourth. Now we can find ix for the whole thing. They are both, now we have both of those rectangles. We have the moment of inertia about the red axes. So now we can add them together. I for segment 1 plus I for segment 2. And so that's going to be 41.75 plus 37.5, and we end up with 79.25 inches to the fourth. That is a number we can take to the bank. That's the number we would use to calculate the deflection of that floor slab in Marquez Hall, in Coors Tech, or whatever project we're working on. That's the number we would use to calculate our deflection of that floor slab. So make sure you do each rectangle separately and then add them up at the end. Sorry I went over there.